Number 10. The island that kept erupting after everyone assumed the worst was over. Off the southwestern coast of Iceland, in the North Atlantic, where the water runs black and cold, there is a small fishing island called Heimaey. It sits at the southern tip of the Vestmannaeyjar archipelago, and for most of its history, it was known as the most productive fishing port in the entire country. Nearly 5,000 people lived there in January of 1973. They had fish processing plants, tightly packed wooden homes, a harbor protected naturally by the island's geography, and no reason whatsoever to believe that what was about to happen could happen at all. There was no known active volcano on Heimaey. The last eruption in the Vestmannaeyjar region had occurred offshore and underwater in 1963, creating an entirely new island called Surtsey. That event was dramatic, scientifically significant, and entirely removed from where people lived. It had not threatened anyone. It had not destroyed any homes. It had, in fact, become a point of national pride. So, when the ground on Heimaey cracked open on January 23, 1973, at around 1:30 in the morning, the population had received no warning and had made no preparations. The fissure that opened that night ran for roughly 2 kilometers across the eastern side of the island. It produced a curtain of lava fountains that witnesses described as a wall of fire rising into the darkness above the houses. The timing, by some accounts, carried a grim irony. Nearly the entire fishing fleet was in port that night because of a storm the previous day that had kept boats from going out to sea. That idle fleet became the evacuation fleet. Within hours, the fishermen and their families were loading whatever they could carry onto trawlers and ferrying people to the mainland. The evacuation was remarkably swift, and the overwhelming majority of residents were off the island by the morning after the eruption began. That organizational achievement almost certainly saved hundreds of lives, but it did not save the island itself. What followed over the next 5 months was a slow grinding destruction that the residents watched from the mainland. Lava advanced toward the harbor, the island's economic lifeline. The Icelandic government made an extraordinary decision. They would try to stop the lava using seawater. Pumping operations began in February, spraying millions of gallons of cold ocean water onto the advancing lava front in an attempt to cool and solidify it before it sealed the harbor entrance. Volcanologists and engineers worked alongside fishermen and municipal workers in conditions that were, by any measure, extreme. Ash fell continuously. Toxic gases seeped from the ground. Buildings were buried under meters of volcanic debris. The operation lasted for weeks, and the results were genuinely debated. Some researchers argued the cooling effort made a measurable difference in slowing the lava's advance. Others were less certain whether the natural cooling of such a large flow would have achieved a similar result regardless. What is clear is that the harbor was not sealed. It survived. Narrower than before, but functional. Over 400 homes were destroyed. About 1/3 of the town was buried under lava or ash. An entire new section of land was added to the island's eastern coast, where lava had poured into the sea. When residents eventually returned, some of the buried buildings were excavated, their contents preserved under volcanic material, much the way Roman buildings were preserved at Pompeii. The excavated site is now known informally as the Pompeii of the North. Heimaey recovered. The fishing industry resumed. Most residents came back, but the eruption had fundamentally altered the island's geography and permanently changed how Icelanders thought about the volcanic risk beneath their own communities. The danger, it turned out, did not need to be a known volcano. It only needed to be the ground itself. What happened on Heimaey was survivable because the fleet was in port. The next entry on this list is about a place where no such luck existed, and where the mountain had been giving signals for years before it finally moved. Number 9. The mountain that scientists were watching when it killed them anyway. On the morning of May 18, 1980, geologist David Johnston was stationed at a monitoring post roughly 8 miles north of Mount St. Helens in Washington state, in the Pacific Northwest of the United States. He had been there for weeks, part of a United States Geological Survey team, tracking the volcano's increasingly alarming activity. Johnston was young, experienced, and fully aware of what he was observing. Mount St. Helens had been shaking with earthquakes since March of that year. A bulge had been growing on its northern flank at an extraordinary rate, pushing outward by as much as 2 meters per day. Steam venting and minor ash eruptions had already forced evacuations and exclusion zones. Johnston and his colleagues had been arguing, in some cases urgently, for wider evacuation perimeters. They understood the volcano was building towards something significant. They did not know precisely when, and they did not know the exact mechanism that would make it so catastrophic. At 8:32 in the morning, a magnitude 5.1 earthquake struck directly beneath the mountain. The northern flank, weakened by weeks of internal pressure, simply gave way. The entire bulge, which had grown to enormous proportions, collapsed in what geologists call a sector collapse, the largest landslide recorded in human history. The collapse depressurized the magma system beneath the volcano almost instantaneously, triggering a lateral blast of superheated gas, ash, and rock that traveled northward at speeds estimated between 300 and 700 kilometers per hour. The blast reached Johnston's observation post in seconds. His last recorded transmission was brief. Vancouver, Vancouver, this is it. His body was never found. The blast zone covered approximately 600 square kilometers. Trees were flattened or stripped entirely across an area that, in aerial photographs taken afterward, looked like the surface of another planet. The eruption that followed the lateral blast sent a column of ash 24 kilometers into the atmosphere. Pyroclastic flows, dense avalanches of superheated gas and volcanic material swept down the mountain's flanks. Lahars, volcanic mudflows, traveled down river valleys for dozens of kilometers, burying bridges, roads, logging camps, and portions of river systems under meters of gray debris. The North Fork Toutle River carried so much volcanic material into the Columbia River that shipping channels required emergency dredging. Ash fall from the eruption blanketed communities across eastern Washington, Idaho, and Montana. In some towns, midday became as dark as night. 57 people died, including Johnston, and a lodge operator named Harry Truman, who had famously refused to evacuate from the shores of Spirit Lake, and whose body, like Johnston's, was never recovered. The volcano had removed a significant portion of its own summit, dropping the peak's elevation by approximately 400 meters in a matter of seconds. What makes the St. Helens eruption particularly significant from a disaster study perspective is precisely the fact that it was being watched. The scientific community knew an eruption was coming. They had instruments on the ground, helicopter surveillance, and a deep understanding of the geological history of the Cascade volcanic arc. The failure was not in detection. It was in the physics of the lateral blast itself, which was far more powerful and far more directional than anyone had fully anticipated for that style of eruption. The exclusion zone, which had already been controversial because local business owners, loggers, and residents had pressed authorities to narrow it and allow some economic activity to continue, was in several places smaller than the blast's actual radius. Johnston himself had advocated for wider zones and had not received full support for that position. The record of those internal debates survived him. He did not. The geology of the Pacific Northwest had produced catastrophes like this before, and would produce them again, but not all of the volcanoes on this list waited for scientists to have instruments ready. Some struck civilizations that had no framework for understanding what was happening to them at all. Number 8. The eruption that a Bronze Age civilization watched from their ships and could not explain. Somewhere around 1600 BCE, give or take a few decades, depending on which dating method researchers use, the island of Thera in the Aegean Sea experienced one of the largest volcanic eruptions of the past several thousand years. Thera, which today is the island group known as Santorini, was at that time a place of substantial habitation. Archaeological excavations at a site called Akrotiri on the southern part of the island have revealed a sophisticated Bronze Age settlement with multi-story buildings, indoor plumbing infrastructure, elaborate frescoes depicting ships, landscapes, and human figures, and material evidence of significant trade connections with Minoan Crete, Egypt, and Cyprus. The people who lived there were not an isolated community. They were part of a broader Aegean trading world, and their island was, by the standards of their time, prosperous. The excavations at Akrotiri, led most notably by the Greek archaeologist Spiridon Marinatos, beginning in 1967, uncovered something striking. The site was abandoned before the final catastrophic eruption. There are no human remains in the excavated areas. There are no valuable metal objects. The inhabitants appear to have left in an organized manner, taking their portable wealth with them. This suggests there were warning signs, likely in the form of earthquakes and preliminary volcanic activity, that gave the population time to evacuate. Where they went is not known. Whether they survived is not confirmed. The final eruption, when it came, was enormous. Estimates of the eruption's volume vary, but it is generally placed among the largest volcanic events of the Holocene epoch. The caldera that now defines Santorini's characteristic crescent shape, the one that tourists photograph from white-walled cliffside restaurants, is the collapsed remnant of what was once the central volcanic cone. The eruption almost certainly produced a massive tsunami that struck coastlines across the eastern Mediterranean. Geological evidence of the tsunami has been found in sediment deposits on various islands and in parts of the eastern Mediterranean coastline. The scale of the ashfall was significant enough to leave traces in ice cores from Greenland and in sediment records from the sea floor. Some researchers have attempted to connect this eruption to the decline of Minoan civilization on Crete, arguing that the tsunami damage, the disruption to trade networks, and the psychological impact of the catastrophe contributed to Minoan vulnerability in the decades that followed. That connection remains debated, and the timeline of Minoan decline relative to the eruption's precise date is not cleanly established. The evidence supports a connection of some kind. It does not definitively prove cause and effect. What is not debated is the scale of destruction. The island of Thera itself was fundamentally transformed. A large central portion of it simply no longer exists. It collapsed into the emptied magma chamber, and then the sea filled in what remained. The frescoes from Akrotiri, preserved under meters of volcanic pumice and ash, are among the finest surviving examples of Bronze Age Aegean art. They show a world that was sophisticated, colorful, and deeply connected to the sea, painted by people who had no way of knowing that the ground beneath their painted walls was already preparing to eliminate everything they had built. The danger was not strange to them. It was the island itself. The Aegean eruption buried a civilization and reshaped a sea. But there is an eruption from the ancient world that buried something else entirely, an empire's confidence in its own permanence. Number 7. The afternoon when a Roman resort city discovered that fame offered no protection. Pompeii, in the late summer of 79 CE, was not a city in decline. It was a thriving, densely populated Roman urban center on the Bay of Naples, sitting roughly 9 kilometers from the summit of Vesuvius. It had a forum, an amphitheater, multiple bathhouses, taverns, brothels, temples, bakeries, and a commercial harbor that connected it to broader Mediterranean trade. Herculaneum, smaller and wealthier, sat even closer to the mountain, approximately 7 kilometers from the summit. The population of the two cities combined has been estimated in the tens of thousands, though precise figures are impossible to confirm. The people living there in August of 79 CE had every reason to feel secure. Vesuvius was not understood to be a volcano in the modern sense. It was simply a mountain, a green, fertile mountain whose slopes were covered with vineyards and farms that produced some of the most valued wine in the Roman world. There had been a significant earthquake in the region in 62 CE, 17 years earlier, that had damaged both cities substantially. Reconstruction was still ongoing in some areas when Vesuvius erupted on the 24th of August, 79 CE, or possibly late October of that year, depending on how one interprets newer archaeological evidence, including food remains and a charcoal inscription found in a house under excavation. The dating debate is genuinely ongoing in the scholarly literature. What is not debated is the sequence of destruction. The eruption began with a vertical column of ash and pumice that rose to approximately 30 kilometers in height for several hours. Pumice fell on Pompeii like a heavy gray rain, accumulating on rooftops, in streets, and in the spaces where people had taken shelter. Many people died when rooftops collapsed under the weight. Others attempted to flee and were caught on the roads. Some hid in buildings that subsequently collapsed. Then, in the early morning hours, the eruption column destabilized and collapsed, generating pyroclastic surges and flows that swept down the volcano's flanks at extreme temperatures. Herculaneum, which was not heavily affected by the initial pumice fall due to wind direction, was hit by these flows first, and with particular severity. The pyroclastic material that buried Herculaneum reached temperatures high enough to instantly kill anyone who had not already evacuated. Skeletal remains discovered in boat storage chambers along Herculaneum's ancient shoreline, found during excavations in the 1980s, showed signs consistent with extreme thermal shock, suggesting near instantaneous death from the surge's heat. Pompeii received its own deadly flows in the hours that followed. The famous plaster casts of Pompeii, first created by archaeologist Giuseppe Fiorelli in the 1860s, are made by pouring liquid plaster into voids left in the hardened volcanic debris by the decomposed organic material of human and animal bodies. The resulting forms are not statues. They are the preserved three-dimensional shapes of people and animals at the moment of death, captured in the exact posture they held when the pyroclastic material solidified around them, a dog straining against its chain, a man covering his face, a family clustered together in a back room. The record preserves the shape, not the name, of the people trapped beneath it. Vesuvius buried not just cities, but the entire lived texture of Roman daily life, accidentally preserving it for nearly 2,000 years under meters of volcanic debris. The eruption that took Pompeii was enormous, but contained within a limited geographic area. The next entries on this list involve eruptions that were not contained, that did not stop at cities, that altered climates, collapsed governments, and killed people across continents. Number 6. The volcano nobody remembers that may have helped end an empire. In 536 CE, the sky across Europe, the Middle East, and parts of Asia went dark. Not briefly, for most of that year and into the following years, a mysterious dry fog filled the atmosphere, reducing solar radiation and dropping temperatures across the northern hemisphere. Crops failed, livestock died, famines broke out across the Byzantine world, across China, and across regions where detailed records were kept. The Byzantine historian Procopius wrote that the sun gave forth its light without brightness, and appeared like the moon throughout the whole year. Medieval chronicles from Ireland recorded a failure of bread in 536 CE. A Mesopotamian chronicle described the sun darken. Tree ring data from multiple continents shows a severe growth anomaly beginning in 536 CE, one of the most dramatic cold periods preserved in the dendrochronological record for the past 2,000 years. The source of this dimming was for a long time debated. The leading hypothesis, now supported by ice core analysis from Greenland and Antarctica, is that a massive volcanic eruption around 536 CE injected enormous quantities of sulfate aerosols into the stratosphere, creating a reflective veil that reduced sunlight reaching the Earth's surface. Additional eruptions in 540 CE and 547 CE compounded the effect, producing what climate scientists and historians refer to as the Late Antique Little Ice Age. The identification of the specific volcano or volcanoes responsible is still an area of ongoing research, with candidates including sources in Iceland and in the northern hemisphere high latitudes. The precise location of the 536 eruption has not been definitively confirmed. What was confirmed were the consequences. The climate disruption of the mid-6th century coincided directly with the outbreak of the Justinianic plague beginning in 541 CE, which was the first documented pandemic of Yersinia pestis, the bacterium responsible for bubonic plague. The connection between the climate shock and the plague's emergence and spread is a subject of serious historical and epidemiological research. The argument, supported by historian Kyle Harper and others, is that the famine conditions weakened populations and disrupted trade networks in ways that may have created conditions favorable to the plague's spread. The Justinianic plague killed millions across the Mediterranean world over the following 2 centuries, and significantly undermined the Eastern Roman Empire's ability to project power and hold territory. The empire's famous reconquest campaigns under Justinian, which had briefly re-established Roman control over North Africa and Italy, stalled and eventually reversed in the decades following the plague's arrival. The volcano did not directly kill the empire, but the climate shock it triggered set in motion a cascading sequence of famine, plague, and political collapse that reshaped the Mediterranean world for centuries. The eruption's name is not remembered. Its date is approximate. The volcano that caused it may never be identified with certainty. What survived is the tree ring data, the ice cores, the dimmed sun in the chronicles, and the shadow of collapse it left across multiple civilizations simultaneously. There are volcanoes on this list that buried things more concrete than confidence, and more measurable than imperial ambition. The next one buried an entire landscape, and did so in geological time that humans could only read backward. Number 5. The eruption that turned a populated valley into a graveyard that no one found for centuries. In the year 1600, the Huayna Putina volcano in what is now southern Peru produced the largest volcanic eruption recorded in South American history. The eruption began on February 19th of that year, and the effects were felt almost immediately at a regional level. Nearby towns, including Quinestacas and Ubinas, were buried or heavily damaged. Lahars, the volcanic mudflows that are among the deadliest secondary effects of large eruptions, traveled down river valleys at catastrophic speeds, burying agricultural land and settlements under thick deposits of debris. The surrounding region, which had been densely farmed and inhabited, became a landscape of gray ash and hardened volcanic material that took generations to partially recover. The human cost at the local level was severe. Entire villages were documented as destroyed in Spanish colonial administrative records from the period, which provides an unusually well-documented view of the immediate aftermath compared to some ancient eruptions. The Spanish colonial government of the Viceroyalty of Peru recorded the damage and the need for emergency assistance, which allows historians to trace at least the administrative response to the catastrophe. The indigenous population of the region, already under significant pressure from the colonial system, from disease, and from forced labor obligations, faced the additional devastation of a major volcanic eruption, destroying the agricultural land on which they depended. But the Huayna Putina eruption did not confine its effects to Peru. The sulfate injection from the eruption into the stratosphere triggered a documented period of climate anomaly across the northern hemisphere. Tree ring and ice core data shows a significant cooling event in 1601, and historical records from Russia, Europe, and China describe the same phenomenon: failed harvests, unusual cold, and famine. In Russia specifically, the years between 1601 and 1603 saw one of the most catastrophic famines in the country's history. Some estimates suggest that between 500,000 and 2 million people died in Russia during this period, roughly one-third of the population in some affected regions. The famine weakened the social and political fabric of the Russian state, contributing to the political instability of the early 17th century known as the Time of Troubles, during which the ruling Rurik dynasty's successor, Boris Godunov, lost legitimacy amid the starvation and civil unrest. The linkage between Huayna Putina and the Russian famine is supported by the temporal correlation of the eruption's volcanic winter effects with the harvest failures documented in Russian chronicles. The mechanism is the same one that operates in every large volcanic eruption. Sulfur dioxide injected into the stratosphere converts to sulfuric acid aerosols, which scatter incoming solar radiation, reducing the energy reaching the Earth's surface and lowering average temperatures during the growing season. For a society dependent on grain cultivation in a climate with already marginal growing seasons, a reduction of even 1 or 2 degrees Celsius can mean the difference between a harvest and mass starvation. A Peruvian volcano buried a South American valley and simultaneously helped unravel a Russian dynasty. The two events shared a cause that neither population could have known about, separated by thousands of miles of ocean and land, connected only by the thin layer of atmosphere they both breathed. Number 4. The year the sun stopped rising properly and the world began to come apart at its edges. In April of 1815, on the island of Sumbawa, in what is now Indonesia, Mount Tambora produced the largest volcanic eruption since humans began keeping written records. The mountain before the eruption stood at approximately 4,300 meters. When it was finished, the summit had been reduced by roughly 1,400 meters. The eruption column reached an estimated 43 kilometers into the atmosphere, penetrating deep into the stratosphere. The sound of the eruption was heard as far away as Sumatra, more than 2,000 kilometers distant, and in parts of Australia, where it was initially mistaken for cannon fire. On the island of Sumbawa itself, and on neighboring Lombok, the pyroclastic flows and tsunami generated by the eruption killed an estimated 10,000 people almost immediately. The surrounding areas of the region experienced ashfall so heavy that it blocked out the sun for several days, and destroyed all agricultural crops across a wide radius. But the local death toll, catastrophic as it was, represented only a fraction of the eruption's total human cost. The Tambora eruption injected a massive quantity of sulfur dioxide into the stratosphere, producing a global volcanic winter that reached its most severe effects in 1816. That year became known in the historical record across Europe and North America as the year without a summer. In New England and in parts of Canada, killing frosts occurred in June and July of 1816. In June, a snowstorm struck parts of the northeastern United States. Crops that had been planted failed. Grain prices rose sharply across Europe, where the agricultural system was already strained by the disruptions of the Napoleonic Wars, which had only just ended with the defeat at Waterloo in June 1815. The combination of post-war economic dislocation and the Tambora-driven harvest failures produced widespread famine across Europe and parts of Asia. In Ireland, the harvest failure contributed to a typhus epidemic that killed tens of thousands. In Switzerland and Germany, food prices rose to levels that provoked food riots. Across China, particularly in the Yunnan province, the cold disrupted rice cultivation and contributed to widespread hardship. Estimates of the total global death toll attributable to the famine and disease consequences of the Tambora eruption range from roughly 70,000 at the low end to as high as 200,000 or more in some analyses, though precise figures for population-level excess mortality in this period are difficult to establish with certainty. There are other cultural traces. The summer of 1816, unusually dark and cold, was the summer during which the poet Percy Bysshe Shelley and his companion Mary Godwin, along with Lord Byron, were sheltering at the Villa Diodati on Lake Geneva in Switzerland, unable to enjoy the outdoors because of the relentlessly gloomy weather. Byron's poem Darkness was written that summer, describing a world where the sun had been extinguished, and during those miserable, cloud-covered evenings, the group held a ghost story competition that produced, from the 18-year-old Mary Godwin, the first draft of a story about a scientist who created a being out of dead matter. That story became Frankenstein. The connection between Tambora and Frankenstein is a historical coincidence well documented by researchers including Gillen Darcy Wood, who examined the eruption's cultural and social consequences in depth. It does not require exaggeration. A volcano on an island in the Indonesian archipelago altered the northern hemisphere's climate and in doing so put a group of writers indoors on a lake in Switzerland on a summer evening when they should have been walking in sunlight. Tambora's scale was staggering, but the entry at number 3 involves a volcanic event that produced consequences not over months or years, but that altered the history of an entire ocean basin and a colonial empire over decades. Number 3. The mountain that collapsed into the sea and sent a wave that governments refused to understand until it was too late. On the morning of August 27, 1883, the volcanic island of Krakatau, situated in the Sunda Strait between the Indonesian islands of Java and Sumatra, underwent a cataclysmic series of eruptions that culminated in what is believed to be one of the most powerful volcanic events in recorded history. The island had been erupting at increasingly intense levels since May of that year, and the Royal Dutch Navy had even sent a vessel to observe the activity in late May, with the crew describing impressive but not alarming volcanic displays. The local population had been watching the eruptions with a mix of curiosity and apprehension for months. There had been no significant evacuation of the surrounding coastal communities. The eruption sequence on August 26th and 27th produced a series of explosions of escalating severity. The loudest explosion occurred at approximately 10:02 in the morning on August 27th. The sound of that explosion was heard in places as distant as Rodriguez Island near Mauritius in the Indian Ocean, approximately 4,800 kilometers away, and in parts of Australia and Sri Lanka. It is considered the loudest sound ever recorded in human history, a claim supported by the documented observations from multiple locations at great distances. The eruption column reached heights of approximately 36 to 40 kilometers. The caldera collapse that accompanied the eruption generated a series of tsunamis, with the largest waves reaching estimated heights of 30 meters or more as they struck the coasts of Java and Sumatra. More than 165 coastal towns and villages were partially or completely destroyed. The total death toll is estimated at approximately 36,000 people, the overwhelming majority of whom died not from the eruption itself, but from the tsunamis. The Dutch colonial authorities in Batavia, the administrative capital of the Dutch East Indies located on the northwestern coast of Java, received reports of the disaster in the hours and days following the eruption. The scale of the destruction in the coastal zones of the Sunda Strait was enormous. Entire communities had been swept away. Ships were carried far inland by the tsunami waves. The Dutch steam vessel Bereau was found by search parties approximately 3 kilometers inland from the coast of Sumatra, carried there by the tsunami. Its crew of 28 people had all perished. The colonial administration organized relief efforts, and the eruption was documented extensively, partly because the telegraph network meant that news traveled to Europe within days, making Krakatau one of the first major volcanic disasters to receive near real-time global media coverage. The eruption also affected the global climate. The dust and aerosols injected into the atmosphere produced vivid red and orange sunsets across the northern hemisphere for months afterward. These atmospheric effects were documented and photographed in numerous locations and were noted by scientists who were beginning to understand the connection between volcanic eruptions and climate effects. The eruption of Krakatau contributed to the development of modern volcanology as a scientific discipline and to improved understanding of how eruptions affect global atmospheric conditions. The beautiful sunsets were, in essence, the visible signature of an atmosphere loaded with volcanic debris. The British painter and critic William Ashcroft made hundreds of sketches of these unusual sunset colors from the Thames embankment in London in the months following the eruption. Science and art both recorded the same event from opposite sides of the world. Krakatoa did not end there. The site of the collapsed volcano became volcanically active again in the 20th century, producing a new island called Anak Krakatoa, child of Krakatoa, which emerged from the caldera in 1927 and has been erupting intermittently ever since. In December 2018, a collapse of Anak Krakatoa's unstable flank generated a tsunami that struck coastal areas of Java and Sumatra with little warning, killing more than 400 people. The authorities had not issued a tsunami warning because the triggering mechanism was a flank collapse rather than an earthquake, and the monitoring system was not configured to detect that specific threat. The 1883 catastrophe and the 2018 catastrophe shared the same geography and the same fundamental failure: the assumption that what was known about the hazard covered all of its possible expressions. The ledger of Krakatoa is still open. The entries at the top of this list involve eruptions that did not just kill coastal populations or starve distant continents, but that may have shaped the fundamental trajectory of human civilization itself. Number 2. The eruption that history forgot because it happened before history existed and what it did to everyone who survived it. There is a geological formation in the caldera of what is now Yellowstone National Park in the northwestern United States, a place called the Lava Creek Tuff. Geologists use the term tuff to refer to rock formed from compacted volcanic ash and debris, and the Lava Creek Tuff represents the solidified remnant of an eruption that occurred approximately 640,000 years ago. The eruption produced an estimated 1,000 cubic kilometers of volcanic material, making it one of the most powerful eruptions in Earth's geological record during the period when humans or human ancestors were alive. It was one of 3 major eruptions that the Yellowstone volcanic system has produced in the past 2.1 million years, the others occurring at approximately 2.1 million years and 1.3 million years before the present. To put the scale in perspective, the 1980 Mount St. Helens eruption produced roughly 1 cubic kilometer of material. The Yellowstone eruption was 1,000 times larger. The effect of an eruption on this scale on the human and pre-human populations of North America in that period is not directly recoverable from the historical record, for the obvious reason that there is no historical record from 640,000 years ago. What we have is geological evidence. The Lava Creek eruption deposited ash across most of what is now the continental United States, with significant deposits reaching into parts of the Gulf Coast and the eastern seaboard. The eruption would have generated a volcanic winter of substantial duration, probably years rather than months, severely disrupting vegetation and animal populations across an enormous area. Any archaic human populations in North America at that time, and the evidence for archaic human presence in North America 640,000 years ago is itself limited and debated, would have faced conditions that were, by any measure, unsurvivable in the immediate blast zone and extremely challenging across a vast surrounding region. The broader relevance of the Yellowstone system is what it tells us about the category of eruption known as a supervolcanic eruption, defined by geologists as an eruption producing more than 1,000 cubic kilometers of volcanic material. There are several such systems identified on Earth, and the Yellowstone system is among the most studied. The system remains volcanically active. The caldera region experiences significant seismic activity, has active geothermal features, and is continuously monitored by the United States Geological Survey. The probability of a super-eruption from Yellowstone in any given century is estimated as extremely low, but not zero. The monitoring data is publicly available and is genuinely one of the most closely watched volcanic systems in the world. The reason Yellowstone belongs in a conversation about catastrophes is not primarily predictive, it is historical. The evidence preserved in the geological record tells us that eruptions on this scale have happened on this planet, have happened within the time frame of human existence, and have produced landscape-scale devastation that altered the ecological conditions across entire continents. In at least one case, there is genetic evidence suggesting that an ancient supervolcanic eruption may have drastically reduced human population numbers. The Toba eruption in Sumatra, Indonesia, approximately 74,000 years ago, is the strongest candidate. Toba produced an estimated 2,800 cubic kilometers of material, making it the largest known eruption of the past 2 million years. Some researchers, drawing on genetic population studies that suggest a severe bottleneck in human genetic diversity around this time period, have proposed that the Toba eruption came close to eliminating the human species entirely. This population bottleneck hypothesis is debated, and alternative explanations for the observed genetic data exist, but the eruption itself is not debated, its scale is not debated, its occurrence at a time when anatomically modern humans were present in Africa, and possibly other regions, is not debated. The record preserves the ash layers. It preserves the collapsed caldera. What it cannot preserve is the sound of the world going silent afterward, continent by continent, as the species that would eventually build cities and write chronicles struggled, in the dark, with the possibility of disappearing before they had produced a single word. Number 1. The eruption that may have broken the first civilization and whose shadow reaches into every disaster that followed it. In the summer of 1257 CE, or perhaps slightly earlier in that year, a volcano on the island of Lombok, in what is now Indonesia, produced what modern volcanological research has identified as the largest volcanic eruption of the past 7,000 years. The volcano is known as Samalus, and it is a peak associated with the Rinjani volcanic complex, which is still an active volcanic system today. The identification of Samalus as the source of the 1257 eruption is relatively recent in scientific terms. For much of the 20th century, the eruption was documented in ice cores from Greenland and Antarctica, where it appears as the largest sulfate signal of the past several thousand years, but the specific volcano that produced it was unknown. The mystery was resolved primarily through the work of French volcanologist Frank Levine and colleagues, whose research published in 2013 matched the geochemical signature of the ice core deposits to the tephra, the ejected volcanic material, found around the Samalus caldera on Lombok, and corroborated by a Javanese chronicle known as the Babad Lombok, which describes a catastrophic eruption of a mountain called Samalas. The eruption is estimated to have produced between 40 and 80 cubic kilometers of material, with the sulfate injection into the stratosphere far exceeding that of Tambora or Krakatau. The immediate destruction in the region was catastrophic. The Babad Lombok, acknowledging that this is a chronicle whose precise historical reliability and dating are subjects of scholarly assessment, describes the destruction of a kingdom called Pamatan on Lombok, including the burial of its capital city under volcanic debris. The chronicle mentions that a prince escaped the destruction and that the kingdom did not recover. Archaeological surveys on Lombok have found deposits of volcanic material consistent with the eruption's scale, and ongoing research in the region continues to assess the extent of the immediate human devastation. But as with Tambora and the 1600 Huayna Putina eruption, the most consequential effects of Samalus were felt far beyond its immediate geography. The sulfate injection into the stratosphere in 1257 triggered a northern hemisphere climate anomaly that is well documented in tree ring records, ice cores, and historical chronicles. The years following 1257 saw widespread harvest failures across Europe and parts of Asia, the cooling effect compounded with existing pressures on medieval agricultural systems, which were already operating near their limits in many regions due to population growth over the preceding 2 centuries. The famines of the late 1250s and early 1260s weakened populations across England, France, and other parts of Europe. Then, in 1315, began a catastrophe known as the Great Famine of 1315 to 1322, the worst famine to strike medieval Europe before the Black Death. Historians debate the precise relationship between the Samalus eruption's climate effects and the Great Famine, which began 6 decades after the eruption, and most analyses treat the Great Famine as the product of multiple factors, including a broader shift in climate known as the medieval climate anomalies transition toward the Little Ice Age, the fragility of medieval agricultural systems, political instability, and a series of specific wet and cold growing seasons beginning in 1315. The Samalaz eruption may have contributed to the broader climate shift rather than causing the Great Famine directly. That connection is a matter of ongoing research and is stated here as a hypothesis supported by some evidence, not as confirmed consensus. What is not in dispute is the eruption's magnitude, its timing, and its atmospheric impact, and what is also not in dispute is what came next in European history. The Great Famine beginning in 1315 killed millions. a population already weakened by famine and by the nutritional and immune deficiencies that accompany it was then struck, beginning in 1347, by the Black Death, the most devastating pandemic in European history, which killed between 1/3 and 1/2 of Europe's population over roughly 5 years. Historians including Bruce Campbell and others working at the intersection of climate history and medieval social history have built substantial arguments that the sequence from the 1257 climate shock through the Great Famine through the Black Death represents a connected chain of catastrophe, each link weakening the chain against the next. The Somalis eruption did not cause the Black Death. No single event can bear that weight, but it may have been the first crack in a foundation that took a century to fully collapse. The Babad Lombok says the mountain destroyed a kingdom. The ice cores say it darkened a hemisphere. The chronicles of Europe record the hunger and the plague that followed. None of these sources speak to the same people or the same places, and yet they all describe, from their separate distances and languages and centuries, the long shadow of the same morning, when a mountain on an island in Indonesia broke open and sent its contents into the sky. Every disaster on this list buried something. Some buried cities, some buried harvests, some buried kingdoms. The largest ones buried the conditions that make civilization possible, slowly enough that no one could see the cause and the consequence occurring together, fast enough that by the time the hunger or the plague arrived, the volcano was already forgotten. Tell us in the comments which of these 10 entries you think left the longest shadow, the one whose effects reached farthest across time and distance. And if this kind of dark, forgotten history is what you want more of, subscribe to the Catastrophe Ledger.